you doing? I'm Mr. Rose, and today we're going to talk a little bit about energy of a capacitor, and again, another conceptual question, but also really trying to understand what these capacitors are doing, right? A capacitor essentially is a device that stores up charge. So one more time, this problem comes from our text University Physics. It's the 13th edition and Young and Freeman, and I've printed out a copy of the question. This is question 24.7. Same advice as always. You should really read over this question, see if you can come up with your answer, and then see if it matches with what I say. So, in this question, get to my board here. Now, the question's asking us, as we're changing things, what's going to happen to the electric field, the electric potential, and my total energy, right? So, question 27 again, the first thing we're doing is we're connecting a parallel plate to a potential difference, and then we're disconnecting it. Now, a capacitor does something. It stores up charge. When I disconnect the potential difference from my capacitor, I still have charge unless I physically discharge that capacitor. So when I disconnect the battery, as it says here, the battery is disconnected. Well, when I do that, my charge Q, I guess I'm going to write it in a different color. First thing I want to know, or I want to note, is that Q remains the same, right? Q isn't going to change because I took the battery off. My charge is stored up. Now, how am I going to relate that to the electric field? What is going on with my electric field? Well, if we remember, right, if this is a parallel plate, say just one of my parallel plates, I've got a surface area here. And I can relate Q to a charge in an area, or more importantly, if I recall, I can say I have some sigma that is a charge per unit area. Now, why is this going to be helpful? Because I remember things from my Gauss's law that the electric field between two parallel plates, and if you don't remember it, I suggest that you go back and reprove it. But my electric field between two parallel plates is sigma divided by epsilon 0. Now, epsilon 0 is a constant. My charge isn't changing. My area of the plate isn't changing just because I'm separating the distance out. So sigma doesn't change, which means my electric field has to stay the same. So for this first part, electric field remains the same. Nothing happens to the electric field as my separation distance increases. Again, I am going to make this disclaimer, or I'm going to assume that we're going to keep a uniform electric field in between. If we get to that fringe effect, again, that might not be 100%. So now that I know what happens there, I want to know what happens to my electric potential as I double the distance. So I want to recall that my electric potential is electric field times distance. And we just figured out that my electric field is going to be the same no matter what. So my potential is going to be directly proportional to my distance. So I can set up a proportion of V1 compared to V2 when I separate it out, how that compares to distance 1 divided by distance 2, my new distance, when my distance is getting bigger. And I'm going to define that distance 2 is 2 times distance number 1. So now I can just direct substitute in here. I can say that my electric potential 1 compared to my new electric potential is going to be D1 over 2D1. That seems to make a little bit of sense. Cross out my D1s. I can cross multiply, and I can say that my new electric potential, V2, is going to be twice that of it was before I separated out my plates. So hopefully that makes a little bit of sense to you. And again, my electric potential, or that push, so to speak, is doubling as the distance is increasing. So what lastly is going to happen to my potential, or my total energy? We're going to do the same thing here. Now, we might not have been this far in class just yet, but I can get a new color. I'll go back to the black marker. Black marker doesn't work so well. Try this brown one. We're going to say that that my potential energy of the capacitor, U, right there, still energy, is equal to 1/2 times Q times my potential. And we've already discussed this. What happens to Q? Nothing happens to Q. Q remains the same. And we're doubling our distance. So I'm not going to go and redefine things. I'm going to make the same proportion. I'm going to say my initial, I don't want to put that, looks like a V, my initial compared to my new spot. Again, Q stayed the same, so I kind of just dropped them out. I don't really need to if I don't want to. But my potential energy 1 compared to potential energy 2 is going to be what happens to my distance at 1, because that's my initial potential energy, compared to my new distance, which we've already defined as 2d1. And here we should see we have the exact same proportion, so my new potential energy is going to be twice that of my old potential. So if I double that distance or triple my distance, we can see there's a direct proportional relationship. So hopefully you're starting to understand what these capacitors do, how they work, and some of their abilities. Specifically, once we charge a capacitor, it stays charged. When we're changing the orientation, obviously that's not going to change my charge, so it's not going to change my charge per unit area. And we can increase or decrease the energy based on just some separation distance. That's all we have for you today. Please feel free to like, comment, or subscribe if you're actually on the YouTube channel. If not, go to my YouTube channel and like, comment, or subscribe, and you'll see me next time.